Okay, so now we are going to use the BDG, the Barkholders-Davies-Gunde inequality. So we generally call this BDG inequality. So what is that? So this BDG inequality says that if we have a continuous local martingale M, then for each small m positive there exist constant small k m and capital K m, okay, non-negative I mean positive constants, such that this expectation can be upper bounded and lower bounded by some constant times expectation of this mth moment of the quadratic variation at capital T. So let us read this carefully. What is m star capital T? M star capital T is actually this thing, that m of small t mod and then take maximum or suprema over all small t between 0 to capital T. So as capital T increases, m star t is non decreasing, correct? It increases. Okay. So this is a very large number, correct, because 0 to t, if you look at, and in between the martingale can be very large also. Okay. There is always some probability that it would be a very large thing. Okay. And then finding out its 2mth order moment. Okay. So that can be estimated using the mth moment of only quadratic variation at capital T. Okay. So this is the statement of BDG inequality for scalar valued local martingales, but there is also a vector version. If M is say RD valued continuous local martingale, then also one can write down that thing. So here instead of this we would write down the norm here. So norm M star T capital T, that is actually supremum of the process in the interval 0 to capital T. So that to the power 2m expectation, that means the 2mth order moment of that random variable. So that is greater or equals to small k m times expectation of that I is equal to 1 to d, since there are d number of components, I is equal to 1 to d, and then quadratic variation of m I at time capital T, and then this whole sums is a random variable. We look, and this is the mth order moment of this random variable. And here similarly on the right hand side also we have this this m is barely visible, but m is here. So it is also the same thing. Okay. So this mth order moment of this random variable. Okay. So some constants multiple of this mth order moment of this random variable can bound this 2mth power of 2mth power moment of this maximum achiever of this mth random variable. Okay. So we are going to use this thing. So here we understand that why is it so important for our case, because we really came across that type of maximum etc. here. Okay. So we need to use this. Okay. And for our case also we encounter the vector valued process. So here for example Brownian motion is a vector valued, this is a matrix. So this is a vector valued process. Okay. So we consider this term now. So expectation of maximum 0 to t of this to the power 2m. Why am I doing this? Because this is as a function of s is a martingale, continuous martingale. Okay, because sk is defined such that this is bounded inside that. Okay, so what we do is that we take this expectation of this 2mth power of this quantity. that is using Bdg's inequality is less than or equal to some constant. Okay. So, this Km I am writing down here as C double prime. Why? Because C prime I think I have used somewhere. Yes, I have used here. So, do not bother much about m n here, because most of the cases this n is d. Okay. So, till now I did not talk about any sequence. Okay. I actually want to write down every n as d, because later I would really use n as a index for sequence. So, this d. Okay, this is d. Okay. So, here C double prime m d actually. Okay. Expectation of maximum 0 to t integration 0 to s minimum s k sigma u x d w to the power of 2 m is less than or equals to C double prime m n expectation of 0 to t minimum s k and sigma u x whole norm square du to the power of m. How did I get it? Because this is the quadratic variation term, correct. So, this term, if I look at this term, okay, instead of capital T, if I replace that by s minimum s k, I would get this term, correct. This is the quadratic variation of this term of this local martingale. So, here now when we get this term here, Brownian motion does not appear here. So, we are in a better shape here. And now again, as earlier, we are going to use I mean either appropriate Heller's inequality or Jensen's inequality. Okay. So, like to the power m, this m is 1 or more. So, this is convex function, I mean positive. So, this is convex function, and then this part just is not unit interval, but we can actually divide and multiply to make it that way, and then we would get t minimum s k to the power of minus 1, but that is less than or equals to just if I write down t to the power m minus. So, that is okay. So, that we do. So, here we are going to get this m also would come here inside 0 to t minimum s k norm of sigma u x whole to the power of 2 m du. Okay. So, here this is the important thing what we were looking for here. We wanted to get one upper bound, we have obtained here. Okay. So, which does not involve Brownian motion. Now, we write down this whole thing as psi k. Okay. So, this thing, see this maximum of 0 t minimum s k excess to the power of 2 m. Okay. So, this 0 t minimum s k excess to the 2 m. So, what appears there on the top? So, I have written that, but I have taken expectation. Okay. This was a random variable, okay, here in this side. Okay. And now, what I do, I take expectation of that. Okay. So, expectation. So, I need to do expectation, because with expectation only we have obtained that upper bound here. So, we need to do that. So, we call this psi k, just writing this so that we can use this same thing, this notation later to obtain one inequality involving psi k. So, this inequality. So, and this depends on k, correct. So, we write down psi k. Also, it depends on t. So, psi k of t. Okay. Also, it depends on m, but we are suppressing that involvement because we are fixing m, correct, because that was assumption that there exists some n for m for that x naught has moment, finite moment of order m. So, that m is fixed anyway from the beginning. Okay. So, I mean here I confirm that these are all dd. Okay. So, now less than or equals to C triple prime. So, the another constant. Okay. Why am I writing another constant? Because I am going to sum these terms, because this is the expectation of integration, you remember, and then for b also we have obtained that some integration 0 to t ds. So, all these integrations are there. So, we want to club those things together. So, here if we want to do that, then all this constant should also be readjusted. So, imagine that we have done that, C double prime triple prime Mn is readjusted this thing, and small t etc. we do not bother much about, because here that finite time interval only we are looking at. So, small t is always less than or equal to capital T. So, we are going to get that. So, expectation of norm of x naught to the power 2 m plus some another constant times expectation of 0 to t minimum s k norm of b to the power 2 m, and then from here sigma norm of 2 to the power 2 m, and then du. Okay. So, this part is not appearing, but this is just du is written here. So, that we obtain, that is true for all small t. So, this psi k t is a function which satisfies this thing here. Okay. So, now we use the growth condition. Okay. So, what is given for b and sigma, like the at most linear growth condition. So, when you do the growth condition, what we are going to get? We are going to get that constant L something there, and then I think what was the constant here? Yeah, some small k times this to the power this square. Okay. So, this inside this thing would appear here. So, when you do that, so here we get that that inside this x to the power of 2 m etc. would appear. And by the way, maximum of that thing of expectation is psi k. So, if I replace that by maximum of these things and take expectation inside, because it is non-negative, I can take expectation inside. So, I would get psi k here. Therefore, psi k would satisfy some constant. So, I am writing here, just see here, psi k of t is less than or equals to c times 1 plus expectation of norm x naught to the power of 2 m plus integration psi k u du. Okay. So, all these constants etc. whatever was there in my hand, I can put everything in C, and then we get this inequality. This inequality reminds us that we can now apply Gronoll's inequality to get one estimate of the growth of psi k. Okay. So, we do Gronoll's inequality. So, that would give me that that this thing is there, correct. So, c times 1 plus expectation norm of x naught to the power 2 m into e to the power of c t. So, this c is coming from all these constant whatever we have obtained till now. Okay. So, this thing. Okay. So, this is psi k t. So, what is the intuitive understanding of that? That this expectation, this 2 m power expectation, as t increases, that the solution, that can be very large, and that the probability that it is large is also becoming larger, etc. However, as a function of t, it is dominated by some exponential function of t. Okay. That is a good thing. That is the thing we just obtained here. It is not like that like that to get a bound I have to get c t square or something, that only with t we can get a bound. Or you can think that okay, log if I take, then that is can be bounded by some kind of linear growth function. Okay. So, that is the inequality we obtain, and this is non-negative of course, because it is norm, expectation of norm of something. Okay. Now, we are going to use this thing, correct. I mean in our result. Okay. So, what we are going to do is that we are going to use Fatou's lemma to get k tends to, I mean we are taking k tends to infinity. As k tends to infinity, s k goes to infinity almost surely, that already you have seen earlier. And now psi k, so psi k is this thing, correct. If I now take k tends to infinity here, I have to justify why that limit can go inside expectation. Thing is that since this is a non-negative random variable, okay, so I can use the Fatou's lemma. Okay. So, Fatou's lemma says that that limit of integration of non-negative random variable. Okay, so that thing is greater or equals to integration of the limit of the integrand. Okay, so expectation is our integration here, correct. So here this limit was taken. So expectation of limit of integration integrand, okay, is less than or equals to the limit of the expectation, but the limit of expectation, okay, so this is the expectation, its limit is less than or equals to this term anyway, and that does not involve k. So this is directly written as it is. So what we have obtained is that now we are free from that localization, that sk. Okay, sk, that localization was used just to ensure so that we can do the analysis whatever we wanted to do. Now we are free from this sk. So you have obtained that this expectation of this thing is less than or equal to this. Okay, so let us see that this is the property what we have aimed to prove. Expectation of this thing, this thing is maximum of excess to the 2m, okay, less than or equals to this thing. Okay, that we have proved now. This thing I am not doing here because this would be easy consequence from, I mean, it is not far different from this part, but anyway, I am not doing it here because only this part would be required to prove the general Feynman-Kac formula. So we are good to now start proving Feynman-Kac formula. So what we do is that, so let us since we have seen that formula before, so let us recall what was the problem, that this was the Cauchy problem. Okay, so in this Cauchy problem we have variable coefficient second order partial differential operator, and if this has a classical solution having at most polynomial growth, then that classical solution has this stochastic representation. Okay, so this is the thing we want to prove. And now as we have mentioned earlier that anyway we are going to use Ito's formula for this. Okay, so what function we are going to do, okay, we are going to take for applying Ito's formula. So we take this v into e to the power of minus t2s, this thing. Okay, we consider this function for taking Zero's formula. So whenever one applies Zero's formula, one should be careful that, okay, whether, I mean, this is applicable here. So first thing is that whether this is sufficiently smooth so that you can operate all the operators. Second thing is that what the local martingale you are going to get. Okay, so is it a martingale, otherwise you would not be able to take expectation 0, etc. So these are the things we need to be careful. For smoothness we do not need to worry because V is already assumed to be a classical solution of the PD. So it already has the desired smoothness, it is already in the domain of the operator. Okay. Since the partial derivative of V is continuous and continuous function on compact set is bounded, so till the time stopping time the partial the domain is in the ball of radius n. So the integrand of the stochastic integral would be bounded, so the stochastic integral would be a martingale. So with respect to time, so s is the time variable, right? T is fixed here. So till time capital T minimum tau n we are going to do, that means s varies from small t to capital T minimum tau n. Okay, what is tau n? Tau n is again so sequence of stopping, a localization sequence, correct. So these are like first exit time for nth ball. Okay, so this n is okay, this is correct n. So this is the sequence we are starting. So all other earlier n's are actually d. Okay, so tau n. Okay, so when we do this, okay, when you take Ito's when you take Ito's formula, you just rule on this, then what are we going to get? We get V of t minimum tau n and here S is t minimum tau n minus V of small t x t, because there is the initial point, small t x t, and then here small t to t, that is 0, actually to the 0 is 1. So, this thing, okay, this difference is equal to then the partial derivative of v with respect to time, and then integration with respect to time, and then partial derivative of v with respect to the space, and the integration with respect to the process, and then quadratic variation and the higher order partial derivative of v and the quadratic variation of x, everything would appear. And from that already we know that what would be those terms, and those terms already arise in the expression of the operator script a, okay, and we know that v is a solution of this equation. Already this del v del t term and a t v term would appear in the Ito's formula, and this would be evaluated at s comma x s and integrated from a small t to s minimum capital T minimum tau n. But this, since v solves this equation, so this sum would be equals to k v minus g. And since I have taken k here also, when I would take partial derivative with this time variable, I would also get 1 minus k there. So, this term would be g plus, and then minus k, and this k would cancel also. So, what would remain is just g. Okay. So, this is so what would remain just g. Okay. So, I am not writing the whole details, it is an easy exercise one can do. So, this g, okay, and as I have promised that mentioned that terminal time t minimum tau n, that would appear here. So, that t minimum tau n is written in two terms. Okay. So, these are the things which we have written earlier in details for many for the actual Feynman-Kac formula proof and many other proofs. So, here we are skipping those details, writing the terms which comes up after the manipulations. Okay. So, g appears as g s x s e to the power of minus small t to s k u x u d u. Okay. So, this whole thing is a function of s, okay, and that is integrated ds, and then the left hand side term, there we had so remember that here, I mean this is minus g, but I am writing g here. So, left hand side is also multiplied with a negative sign. So, left hand side should be v tau n x tau n minus v t x. So, minus sign is omitted here. So, v t x, and the minus v tau n, that is taken on this side. So, you get plus v tau n on this side. Okay. But I should have got capital T minimum tau n, but here I am taking indicator function of tau n less than or equal to t. So, when tau n is equal or less than t, then I can ignore t minimum, I can just write on tau n here, but that is not the whole thing. The complement thing also I should write down. So, that is the case when tau n is more than capital T, then tau n minimum t is actually capital T, correct. So, this is the way we, and then v the solution satisfies the terminal condition. So, at capital T terminal condition, v capital T minimum t comma x capital T is exactly f of x capital T. So, that is the reason that we get f here, and here say for this case I get small t to t tau n, here I would get small t to capital T, clear. So, this is obtained using the Ito's rule, okay, on this function. Okay. You can take this as an exercise to actually get this thing, all this manipulation together. You have to write down 2-3 steps to get it. Okay. So, now for g is there, for g we need to look at the growth condition. G has a growth condition, correct, because here for here this g, so this g has yes, so here this is the result, this g has this growth condition. So here when I have stated, actually I have stated two different theorems compactly together. Actually I have followed this Cauchy and Schiff's book, they do that, so I have also kept it, but it is not a very good idea to state two different theorems in the same place. It is saying that if these two follows, then also you get this result, otherwise if these two follows, then also you get this result. But if these two follows, then you use some different technique, if this follows, then you get different techniques, but those different techniques are not too very different, okay, they can be managed together if that no confusion arises. Okay, so here using the growth condition of g and 2.1, that means this thing which we have proved for the first half of the lecture. So these two things we are going to use now, and we use dominated convergence theorem. Here I am writing that thing, that if the other alternative condition holds, that we do not put a growth condition on g but non-negativity, then we can use Morton convergence theorem. So how do we do that? Okay, so term by term, correct? So first term, second term, third term. Okay, so you remember that we need to prove Vtx is equal to this thing, correct? F of xt times e to the power of this thing, that already appears here. Okay, only thing is that tau n greater than capital T appears here, so that we need to just get rid of. And this integration, this thing appears. So here also I have exactly same integrand, see, gsxs gsxs e to the power of minus small t s k. Okay, so e to the power minus small t s k. Okay, only thing is that here I have capital T tau n, here I have capital T. So I need to get rid of this tau n, okay, this tau n from here, then only and this term I need to send it to 0. Okay, so I have to argue that this can go, this should go to 0, because I mean the basic intuition is that as n tends to infinity, tau n increases to infinity, then with probability 1 that the tau n is more than t. So this random variable converges to 0 almost surely. Okay, but the limit is outside. How to take this limit inside, that is only the challenge we are going to discuss. Okay, and then when we justify, then we can do this. Okay. Okay, so you know that, okay, what are the things we need to do with all these three terms. First term we need to send to this term, second term we need to send to 0, and third term we need to send to this thing. Okay. Okay, so let us go back to this thing. So first term, as n tends to infinity, okay, we are pushing this limit inside. How do you do this? Because we are using dominated convergence theorem. How can we do this? We can do this because g has at most this polynomial growth condition. Okay, and then we are using this 2.1. So here this thing is saying that that it is dominated by this term. Okay, so first term, so since g has at most polynomial growth, so we can use that condition there. So and this is anyway bounded by 1 because k is non-negative. So we can take the limit inside to small t to capital T, these things ds, where s is running from small t to capital T. Okay, so that would be the limit here, and then in the similar manner for third term. So that I need to send there, because that tau n tends to tau n tends to infinity. So as n tends to infinity, so one indicator function of tau n greater than capital T is converges to 1 almost surely. So, only thing is that I need to assure that this I can do, but f has at most polynomial growth. So I can use this I mean 2.1 here to conclude that this third term converges here, and for second term we need to show that is converges to 0. Okay, so here also what we do is that tau n less than or equals to capital T is same as probability that excess the norm of excess from small to capital T, okay, that is greater or equals to small n. Okay, I mean otherwise it does not happen, correct, because I mean sometimes it x norm of x is more than n between small to capital T, that is why the tau n is smaller than capital T, because tau n is the exit time of the ball of radius n. So, now this probability we can use Markov's inequality. Markov's inequality says that expectation of a non-negative random variable is less than or equals to the I mean say a times probability that mod x is more than a. Okay. So, this probability is here, and now so this is more than n, and then if you write down n here, okay, so then this, but then this same as to the power of 2m to the power 2m to the 2m here. So, n to the power of 2m times probability of mod x to the 2m is greater than n to the power 2m is less than or equals to expectation of this to the power 2m, correct. So, that is the thing we are using here, and then we take this into 2m this side to get 1 over n to the 2m. Okay. So, now for this we again use the inequality of what we have obtained earlier, that is that a constant times e to the power of c t. Okay. However, I have n to the power minus 2m, as n tends to infinity this converges to 0. So, we can choose this m, okay, sufficiently large, say it's larger than mu. Mu is the polynomial growth polynomial degree, okay, this thing. So, if we choose m is more than this, okay, so then we can there is some, because here we have second term is less than or equal to m times 1 plus n to the power 2 mu into probability of tau n less than or equal to capital T. Okay, because second term has this function g function v here. So, see when we write down here the polynomial growth, we have written the expression, yes, see. So, this v the classical solution of the Cauchy problem what we have considered satisfies at most polynomial growth of some particular order. That order is taken as 2 mu. So, I am talking about this mu here, okay. Mu is just greater or equals to 1. So, this mu we are talking about, and then if we here take m larger than this mu, then as n tends to infinity the second term goes to 0. Okay. So, here yes, here it is actually n. So, yeah, so mod norm of x to the power 2 m. So, here you have n to the power of 2 mu, correct. So, this grows and this decays. If m is larger than mu, then together multiplication goes to 0. Okay. So, this is the end of the proof of the Feynman-Kac formula. Thank you.